I would like to take this opportunity to welcome and introduce our guest speaker for this session, Dr. Jammy Ramesh Rahul. To talk briefly about him, Dr. Rahul has completed his doctorate in electrical engineering from the National Institute of Technology, Warangal, Telangana in the year 2019. Sir has done his MTech in power electronics drives from VIT at Vellore in Tamil Nadu. He has done his BTech in electrical engineering from Gayatri Vidya Parishad College of Engineering, Vishakhapattanam. Dr. Rahul has research interest in Z-source inverters, multi-level inverters, grid connector, grid connected photovoltaic systems. Sir has presented numerous research papers in national and international IEEE conferences. His research papers have been published in renowned international journals and Scopus Index journals. Sir has taught in Pratap University, Jaipur, and Sri Vidyaniketan Engineering College, Tirupati. At present, Dr. Rahul is working as an ad hoc faculty in Electrical and Electronics Engineering Department in National Institute of Technology at Tadepalli Gudam in Andhra Pradesh. Sir, we are delighted to have you as a speaker for this session. I request you to start this session. Over to you, sir.
Thank you very much, sir. Thank you very much for the introduction, sir. One small request, sir. There is a problem with my video. So if in between it's possible, I will start my video, sir.
Yes, sir.
Okay, sir. Okay, sir. Let us start this session, sir. I will share my screen. Is it visible, sir?
Yes, sir. It is visible.
Thank you very much, sir. So, welcome you all. Very good afternoon to all of you. So today I'm going to present the topic foundations of power electronics condition filtering, basically. So we'll be dealing with some of the aspects of power electronics that is required in the electric vehicles. So before going to the actual power electronics requirement and all, let us see to the basics. So coming to the introduction, EVs are proposed as a solution to help increase energy security, improve fuel economy, lower fuel costs, and reduce emissions. Nowadays, they are becoming very popular. Even we know from the two-wheeler segment, even in the recent update that from the Ola also we are getting two new bikes, scooters, that is Ola S1 and Ola S1 Pro something, which has a distance range of around 130 kilometers or even 180 kilometers it seems. So a lot of improvements are being done in the EV sector. Even in the four-wheeler segment, that is cars, we already have several cars like Tata, Nexon, and Mahindra, and also from other companies. So due to this following reasons, they are getting popular. And when compared to the conventional IC vehicles, they are more efficient when we compare to with respect to the well-to-wheel efficiency. What is this? We'll see sometime later. Generally, we say that EV can be considered as a green form of energy. But the thing is, we cannot say it's completely green because there is emission. Whatever the electricity we obtain is primarily generated by coal in our country. Of course, we also have some other fossil fuels like diesel and natural gas. So here, in case of EV, the emission is not from the vehicle side, but the emission is at the rural or the generating end. So this is one aspect. So what we can say is with the penetration of electric vehicles, the urban pollution can be drastically reduced. And we know that here we can see in the graph where around 30%, around 20 to 25% of the pollution is from the transportation sector, which also includes the pollution that is obtained from the flight or the aeroplanes. So this is also one of the major contribution of the pollution. So partly we can say the EV is green form of energy. So one of the critical aspect of the EV here is the energy sources. Generally, we do use the gasoline power, that is power, petrol or diesel based vehicles. In case of EV, we have different energy sources such as batteries, fuel cells, ultra capacitors, flywheels. Some renewable energy sources like PVs are also nowadays utilized. The research is being going on, and some hybrid storage. It may be a combination of battery, fuel cell, ultra capacitors and super capacitors, whatever. So some combination can also be utilized. So batteries are more preferred when you compare with other forms of energy storage. Generally, they are getting more popular as they are reliable, economical, compact, and mature when compared with the other energy storages. So these are some other advantages, which is environment friendly, reduction in dependency on fossil fuels, clean energy, and more efficient. So here we see, before going to this, 1 second. Fuel cell it's also an energy storage, but here we have some constraints in terms of the safety issues. Why? Because for the operation of the fuel cell, we require some hydrogen and other O2 and all. So there are some safety issues, and even the fuel cell technology is quite costly. So that's the reason they are not getting that much popular. So we cannot completely depend on the renewable sources. There should be they may act as the auxiliary source. So the main source may be some energy storage like batteries or ultra capacitors, and these renewable sources can act as an auxiliary source. So here, this particular pic depicts the power and energy density of various sources like batteries, fuel cells, ultra capacitors. So here we have not mentioned the energy, about gasoline, diesel, and petrol, but it is somewhat higher when you compare with this. So this is the desired specification of EV applications. So here you can observe the power density of gasoline. It will be something around here. So what is power density? The amount of power it can give for a unit weight of the energy source. Similarly, the energy density, here it's basically energy, specific energy will be there here in the x-axis. So energy density means the amount of energy it can deliver for unit weight of the energy source. So here, battery you can observe, even though it has some better energy density, but the specific power requirement, it's somewhat low. So among the various sources, here is batteries, we have ultra capacitor here, and capacitor something around here. So the power density is poor. The power density is relatively low when you come for a battery, even though the energy density is sufficiently good. So due to this particular reason, the amount of weight required by the battery for vehicle applications is very high when you compare with the fossil fuels. So this is one such limitation. And the desired specifications for EV lies in this particular range. So there is no particular source of energy which directly meets the EV applications. That is the specifications that is required for the EV applications. Okay. So this has been one of the research topic and research challenges. So coming to the brief history, previously, even in the at the time of 1830s, the concept of EV has been developed, where a primitive version of a basic lead-acid battery and DC motors were extensively used in those days. But the actual commercialization started after this 1880s, and this during this particular period. So during this particular period, um, IC engines also they do exist parallelly, but they were more costly when you compare with the EV vehicles. Why? Because the fossil fuels were not readily available at that time. So that's the reason the amount of electric vehicles were more when you compare with the gasoline power during that time. And even we have some advantages of EV, that is they do not have these falling issues with respect to the gear changing, hand cranking, and noise unpleasant. Even noise will not be there. But later, during the time 1935 to 1970, the cost of the gasoline is coming down. During this particular period, the cost of oil and other gasoline products came down due to the oil discovery in various locations of the world during this particular period. So due to this, the EVs, there is no much development or progress in this particular EVs. And it's an advantage or an honeymoon period for gasoline-powered automobiles. And during the period 1970 to 2010, again, there is an increase in oil price. So again, the focus has been shifted towards EV. So during this period also, they will be heavy, but they are mainly preferred for the demonstration purpose and other things. And during this period, even the people realize that the fossil fuels will not remain for future. They may get extinct over a period of time. And in addition to that, there will be some environmental impact. So slowly during this period, the work or the research on the EVs gain momentum. And one more thing is, during this particular period, the cost of the electronics is very high. Whatever the electronics that is involved to control the speed or whatever, it's very high. But during this period, the cost of the power electronics equipment, the switches, all these things came drastically down. So which enhanced or led to the development of EVs. So in present scenario, here you can see there are different states, countries, their participation in the EV sector. The most dominant part is China, which accounts to around more than 2,000. So here, India is not there in this top 15 list or so. But nowadays, India is also promoting the EV. They are giving a lot of incentives and they are promoting EV. And even most of the automobile companies, they have posted that post 2030 or 2025, they are not going to manufacture the gasoline-based vehicles, that is petrol and diesel-based vehicles. So in future, after 5 to 10 years, there will be a complete domination. This is the expectation that there will be a complete domination of EVs in the market. So this is the present scenario. Similarly, here you can see the time taken to sell 1 million EVs. Previously, from 2011 to 2016, it took around 60 months. And there is a drastic decrease in the time taken to sell off 1 million EVs. So there is increased interest towards the EVs, even for the customers also. Nowadays, we have seen the petrol increase in petrol rates and diesel rates. That also one of the factor which made the people to think towards the EV. So here, these are the few, various initiatives taken by the different countries. And there are various governments throughout the world they have set the target by 2030 that penetration should be by this much amount. They have set some targets with respect to both the segments, vehicle segments. Not only the governments, even the manufacturers, that is original equipment manufacturers, OEMs, have also announced that they will halt the production for the development of the gasoline-based vehicles from their side. So these are the different OEMs and their corresponding action. Even now, if you see, diesel engines are almost being stopped by most of the manufacturers in the present scenario. So it's mainly petrol vehicles used nowadays. Coming to the EV in India, there are various government initiatives from the as a part of the National Electric Mobility Mission Plan. Even the Reva is one of the company which is afterwards acquired by Mahindra and Ether Energy. These are some of the startups which are associated with the development of some scooters and all. Even Tata Motors, Ashok Leyland are even we might have seen from last 3 to 4 months, the Tata Motors have started. I mean, they have got contracts for the buses, transport buses. They have got some contract in different states of India. So these are the various segments with respect to bicycles, scooters, motorcycles, and rickshaws. We have different companies associated with this. Especially in India, we have the Mahindra electric rickshaws, which have been utilized in different parts. We might have seen in different parts of India. Even motorcycles, we have the Indian companies like Ether Energy, Bangalore-based startup company. They have also associated with scooters and motorcycles. So basically two-wheelers. This with respect to the cars. In car segment also we have the Mahindra being dominating. And coming to the off highway or heavy duty trucks like JCBs or the heavy vehicles which is used for the construction purpose. So here in this particular sector, there is no much development with respect to EV because a lot of high rating motors are required here. So only in this particular sector, there is no much domination of EV. I mean, there is no particular interest as of now, but later on it may be spread to. Coming to the powertrain. So basically, the path of power flow from the source to the wheels, we call it as the powertrain. Here we have different types of transmission of power, whether it may be through the typical or the conventional mechanical power transmission powertrain, that is through IC engine based. The other type of transmission is through electric power transmission powertrain, which may be by battery based electric vehicle or fuel cell electric vehicle, or it may be a combination. It may be a combination of electric vehicle, I mean the battery based plus IC engine. So here hybrid means it's a combination of IC engine and some battery or something. So here again we have the other types which we'll see later on: micro hybrid, mild hybrid, full hybrid, and plug-in hybrid. So EV powertrain functionalities. The basic thing is here we require a bidirectional power flow, which is possible by using some power electronic converters, which we'll see. Why there is a necessity of this particular bidirectional power flow, we'll come to know. So powertrain, here these are the different, so here we have the conventional, where the fuel here can be considered as either petrol or a diesel, and here we have an internal combustion engine, IC engine transmission. So this is the conventional vehicle what we have. Here, these two things will come under EV. Here coming to the first part, that is, let us see first this, the battery-based electric vehicle or some fuel-based electric vehicle. So whenever you have a battery or a fuel cell, basically it's a DC source of energy. We get some DC power. So this motor or generator, generally, anyhow we are going to discuss, but generally we use AC motors. We prefer induction motors, mostly for the four-wheeler segment. So as this is a AC motor and here supplies DC, so we require some power electronic conversion, which can convert DC to AC. Okay, so this is a power electronic conversion. And finally, fed to the transmission network. So here hybrid means it's a combination. Here we have the IC engine and here we have some battery-based vehicle now. So it's a combination. So part of it will be taken care by the battery source of energy, and part of it will be taken by the fuel cell, I mean fuel-based or the IC engine. So that's the reason it's hybrid. It's a combination. We know that the typical or the conventional IC are of two types. There's a petrol and diesel engine. Petrol engine generally uses a spark ignited system, which is generally the mixture is ignited by a spark plug. It is well known to the mechanical engineering students. The diesel engine uses a compression based ignited systems. So here if we see the overall losses associated through the transmission from the fuel tank to the wheels, here you can see different. This is standby losses. Around 1 to 8%, where the engine is running but vehicle is not in movement. It's in standby position. So even though there will be some losses, 1 to 8%, there will be some loss associated with the engine. There's engine loss. It's around 69 to 76%. So major contribution of losses. Similarly, at the wheels, we'll be having various parameters, that is aerodynamic drag, rolling resistance, braking resistance. So friction due to friction and other things. So here around you'll be having around 13 to 27%. Even while transmitting from here to here, that is through driveline, again we have around 3% loss. So this is your powertrain, and this is the vehicle related. So these are the losses that are associated in the conventional engine. So let us see for our, as we discussed in hybrid electric, we have various combinations or variants, which is a combination of IC, internal combustion engine, and an electric motor, which is powered by the or driven by the battery. Let us take the first type, that is micro hybrid. In this micro hybrid, uh, so we'll be having IC engine and another small motor. The rating is up to 5 kilowatt. So due to this hybrid combination, we'll be getting a fuel saving of fuel saving of around 10%. So here generally small motor and low size batteries being employed, which generally aids in the start stop function, which assists the or helps the IC engine during the start and stop function. So it will take care about this. And one particular and even we have the regenerative braking facility here. And one particular example, practically Maruti CS car, which is comes under micro hybrid model. And mild hybrid here, the rating is somewhat higher when you compare with the micro hybrid. So around 17 to 15 kilowatt electric rating motor will be employed. So almost other features are one and the same. So here more fuel saving is we'll be able to get around 10 to 20%. So these are the typical Honda Accord hybrid. Even the BMW 7 series hybrid will come under the mild hybrid, which assists the IC engine still better when you compare with the micro hybrid. Full hybrid, here the rating is more than 30 kilowatts. So you'll be getting even the voltage value. Previous case here, the battery voltage levels may be some 12, 15 volts like this, not more than that. But here, as the power rating is increased, correspondingly, the voltage level is also increased, that is around 200 volts. And around 40% saving is possible with respect to the fuel. Okay. And one more thing is here, even though it's a hybrid model, it can operate in pure EV by not taking any energy from the IC engine. So it can operate as a pure EV for some time at least. Full hybrid is capable. So again, here we have some in full hybrid. Again, we have some other variants or types. Okay, and these are, and coming to the merits, it has very low emission, high mileage, and commercially these are available. Demerits has here we need to, proper energy management is required. We have multiple energy sources. One is through battery and one is through other source of energy, that is through petrol or diesel. So proper energy management strategies are required here. Complex control, high cost, and of course here also we are slightly dependent on crude oil anyway. So these are some of the available models like Chevrolet hybrid, Ford, C-Max, Honda, and others. So in conventional engine, we have seen the various losses that are being associated, but with hybrid technology, previously we have seen micro hybrid, all these things. No? By using this, suppose if we go with the micro hybrid model, it eliminates the standby losses. Through this, we can reduce this particular losses. Similarly, if we go with the mild hybrid, this is the first model, mild hybrid, it reduces this particular components like braking and all this, it reduces to some extent. Why? Because when compared with the conventional mechanical braking, in electrical we have a regenerative braking, where generally, suppose if you are, if you are moving on a gradient, maybe up gradient or down gradient, some part of the energy will be transferred back to the source. That is what we call it as regenerative braking. So that's the advantage. There is a part of energy saving. So that's the reason here they are mentioned there is a slight recovery of loss, or the losses can be reduced in terms of the braking loss. Here some part of the losses can be recovered or reduced, you can say. Coming to the fully hybrid, it reduces the losses associated with engine loss. So previously here it's more than some percentage, but here it's around 76%. So by using this particular fully hybrid model, we can reduce this particular amount. As we mentioned, this particular model fully hybrid is capable of completely operating as a pure EV for at least some time. So indirectly, we are completely eliminating the IC engine. And one more thing, in fully hybrid, you can see the power rating. Power rating is considerably high. So part of it, you can say around 40% of the requirement is taken care by the battery. So easily you can downsize. That's we call engine downsizing is possible. That is one more advantage we get here. So overall energy saving can be achieved by using hybrid models, hybrid technology. You can say. So here, further, if we see in hybrid itself, we have series hybrid. It can be connected in different ways. No, one thing what we got is we have a combination of both IC and battery. That's true. That's fine. But it can be connected in different pattern. So coming to the series hybrid, here you can see it's a combination of IC and battery. B represents the battery, and here PEC represents the power electronic conversion. And here we have the motor, and finally the transmission network. You can say. So here they are connected in series fashion. Okay, where sometimes even the battery gets charged from this particular. Here you can consider it as a parallel combination or parallel connection. You can say parallel connection means this IC is directly connected to the transmission network, and here the battery based battery power electronic converter and the motor or generator unit. So M represents the motor, so it's directly connected to the transmission. So both this part and this part they are operating independently. Okay, independently they are directly connected to the transmission. So this we call it as parallel connection. Here there is a combination. So here we are collecting here at this particular end we are collecting both the things, and finally we are feeding it to the motor, but here it's directly being fed. Compound means it's a combination. It's a combination of series and hybrid. Here you can see um, we are combining in a different way. Here battery is being connected to the PAC. Here again we have the uh, source of energy which is connected, and finally through here we are. So it's a combination of here we are using series, and here if you see from this side it's it is almost like parallel. So here also we have both the things. Okay. So here in this particular figure, you can see the socket of the electric vehicles. Suppose we have generally two types of current, the AC current and DC type. Generally in our home through the utility, we get AC. Right? And DC is used for some applications. Suppose the mobile chargers, whatever the mobiles or even the laptops, they are all use DC power. But how do we get the DC? Through the utility, we get AC. And here we use DC for our some applications, some electronic applications like mobile charging, laptop charging, and all these things. So we have a mobile charger or laptop AC adapter in case of laptops. So inside there will be some conversion from AC to DC. It will be converted and suitable voltage. Generally for mobiles and all, it will be maximum 10 volts, 5 volts DC or 10 volts DC. Same is the case with laptop. So here also we have different types of chargers in order to charge the EV. We have AC chargers as well as the DC supply. Okay. So here you can see different type of sockets that are being employed in different countries. Different with different names we call J1172 with different plug types. See in mobile chargers also we have type A, type C, ABC type. No? Similarly here also we have different types. One thing is you can observe more number of plug pins. Whenever we use socket, we have 3 pins, no, phase, neutral, and some ground terminal. But here you can see a more number of plug pins or outlets because actually there are communication channels. These other whatever the other pins we have in addition to the phase and neutral, they are communication pins. Okay, so these communication pins, plays a role or helps during the charging process. So whenever it's connected to the onboard charger or offboard charger, so it estimates the state of charge of the battery. And based, there is some handshaking communication signal that happens generally. Okay. And this GBT is generally used in Chinese countries. And some JEDMO and all these things used in some other countries like Japan and all. I hope you understood the reason behind this because different vehicles might be using different types of batteries. and whose voltages may be different, maybe 200 volts or 400 volts, whatever. So whenever we connect to the charging station, so there will be some communication happens which estimates the state of the charger's battery. Or in other words, in simple words, we can say it's a handshaking communication signal between the onboard charger and the vehicle. So here we have different modes of onboard charger. So this is your EV, electric vehicle. So obviously you will be having some high voltage battery unit. Okay. I think in the next slide. Okay. We have different modes here. The first mode is G2V. That means grid to voltage. 1 second. Okay, this we'll see at the last. There is some question here. Okay, so modes of OBC G2V, that means grid to vehicle mode. Grid to vehicle mode means, see, grid means not the, it's basically the socket. The utility will be there now, that we can consider as the utility of grid. So through this, we will be connecting the socket, the power cable or whatever, and your vehicle or the battery gets charged. Okay, this is the first mode. And B to G mode. V to G means vehicle to grid mode. So vehicle to grid mode means what? The EV can send some power to the utility grid. This is also being adopted in some of the countries, and this is also getting commercialized. See, when do we use this particular mode? Suppose your vehicle is fully charged and you are not going to use today, or you are not going to use for some time. And during the peak load requirements, your vehicle can feed power to the grid. So they will pay you. So you can supply power to the grid during the peak time, and you can make some money. Okay? The vehicle owner can make some money if he's not using the particular vehicle. So this is also possible. But of course, the power requirement should be this is not used in India, but some countries are trying to utilize this particular mode of operation. Okay. Similarly, V to L or V to H. L means here load and H means home. In our homes, generally we use inverters now, because sometimes there might be some power cut and all. Especially in village, this problem is more relevant. So in such cases, in most of the cities, we have inverters, one of the common appliance nowadays. Okay, because we cannot stay even 1 minute without the electricity. So suppose if you have the electric vehicle, then your electric vehicle acts as inverter. So no need to purchase the inverter, separate inverter in your home. This electric, through this electric vehicle, suppose assume that it's in charged condition, you can utilize it for your home, to power your home. Okay, the power of the battery is too high, such that it can support the complete home. I mean, all the loads of your home also it can support. This is a possibility. Similar to vehicle to load. Sometimes if you go to some hill stations or any stations, and you carry some, suppose for the night you stay in some tents and all. So for some small loads like lightning loads or small fans, you can power it through your vehicle itself. Okay. And B2B mode. Especially in India, suppose if you go to some remote areas or rural areas, let us assume that there is no power in that particular, no electrification in that particular area. Let us assume, but your vehicle is almost drained or discharged. Your battery level is discharged. Then in such condition, how to charge the vehicle? Then you can go with the V2V mode, vehicle to vehicle mode, where your vehicle is get charged by another vehicle. So from the vehicle to the your vehicle, it can be the charge can be transferred, or it can be powered. So that possibility is also there. Okay. So so these are the different modes, okay, of your onboard charger. Is there any problem? Okay, fine. So coming to the degree of hybridization, this particular hybrid, mild hybrid, full hybrid, and plug-in hybrid. So coming to the micro hybrid in the stop feature, this as it's here. A mild hybrid, it can support through braking operation. Even it uses some electric. Sir, is it audible, sir? Any issues are there? I doubt with the respect.
No, sir. No, sir. It's
No.
audible.
Okay, sir. Okay, fine. Okay. So here, it has the mild hybrid has some better features when you compare with the micro hybrid. Micro hybrid only takes care, or it has some additional feature only in start stop feature. But here it takes care of the regenerative braking, through which you can save some energy, and there will be some assistance to the IC engine in a better way here. And fully hybrid, as we mentioned, this is capable of operating as a pure EV for some time at least. So no need of IC engine during that particular duration. So that is one additional feature we get through fully hybrid. And plug-in hybrid means whenever we want, we can plug into the onboard charger or some charging station, and the battery can be recharged. So plug-in feature is there here. So these are the various examples with respect to the each category. So plug-in hybrid Chevy Volt. Toyota Prius will come under the fully hybrid. Coming to the well-to-wheel efficiency, where we have discussed in the starting slide. So well-to-wheel efficiency is basically the amount of energy that is being consumed by mining the fossil fuels, refining it, and then back to the vehicle. The amount of energy consumed by the IC engines is much higher if you compare in this particular aspect when you compare with the EVs. Okay. So well to wheel efficiency, it's a combination of well to vehicle and vehicle to wheels efficiency product. Okay. So right from the fuel extraction to the transportation to the supply to the storing in a fuel tank of the vehicle. So it takes care of the start to stop. I mean, from the starting onwards, where we acquire or procure the fuel, it's taken. And the vehicle to wheel efficiency is based on the final use of the vehicle, fuel on a vehicle. So for a typical or a conventional IC vehicle, the well to wheel efficiency here you can see for a diesel engine, it's around 17%. And for a gasoline based vehicle, it's around 14%. So it's quite low because here there are various losses. We have engine losses, we have transmission losses. In the previous things we have seen. Okay. So most of the losses here itself we have from well to tank itself we have most of the losses. Around 16% of the losses. Now here one it's 84% from the well to the tank. So there in the overall system there are various losses that accounts to only 17 to 14% efficiency. If we compare in a pure EV, the well to wheel efficiency is around 27%, which is better, much better, around 10% more when you compare with the diesel engine. And in case of a series hybrid, the well to wheel efficiency is 21%. Similarly, in a parallel hybrid EV, the well to wheel efficiency is around 24%. In case of a fuel cell based electric vehicle, it's around 27%. Which is almost equal to the case of the series hybrid. So from this, we can say the well-to-wheel efficiency is better in all the models, hybrid models or whatever the pure EV we consider when you compare with the conventional IC engine. So this is the overall architecture. So where we have a onboard charger, this is a connector name. So this is the utility or the AC mains through which we have a connector. Generally for mobiles we call it as a cable. No? So here we call a specific connector which connects between the utility and the onboard charger that is present in the vehicle. So here we have a batteries, a series or the parallel connection of batteries, and we have a battery management system. So which is very much needed in order to maintain the voltage and the current within safe operating limits. So generally batteries, anyhow we are going to say afterwards, battery we have various technologies in which lithium ion batteries are more popular and suitable for EV applications. Okay. So this is about the battery management system which we have. And later on it's fed to the powertrain. In powertrain, whatever the voltage we obtain here, the DC voltage obtained here, it is fed to a three-phase inverter. We use three-phase inverter. Why? Because it's generally suitable for your high power applications. So this particular point, what we call it as the DC bus voltage, which is generally maintained constant. Okay. So we'll be having a various control algorithms, and finally the voltage obtained here is to be maintained constant. And this DC voltage is converted into AC by this particular inverter, and this voltage, AC voltage, is fed to your BLDC motor. Okay. So here we'll be sensing various parameters like torque, speed. I mean, here at the output end of your motor, which is finally fed to the vehicle. So here we'll be having different closed loop controls, which senses the various parameters like current, voltage, and all these things, and try to maintain within the limits. Even we have the temperature sensing, and the control pulses that is required for the operation of this inverter. We do obtain with some controller. It may be some D-space controller. I mean, digital signal processor. Maybe a simple microprocessor or microcontroller, or some advanced digital process like FPGA can be used, through which it can be obtained. So here we have one auxiliary battery uh, where uh, this particular voltage will be utilized for some small applications like lightning. The basic things will be there, which are powered by the low voltage, so around 12 volts. So what are the major components? Battery is of course a major one of the major component, EV batteries, which also involves or includes the battery management system, electric drive. Here we have the different power electronic converters that are required. That will see the we have AC to DC, DC to DC, and DC to AC conversions. Coming to the motors, here we have different variants that we'll discuss afterwards. So let us discuss briefly about each component. Coming to the batteries, so the first basic variant is lead acid battery, which are used in previous days and all. Coming to the advantages, it's cheap, easily available, high recycling rates. But the problem is you have poor density, poor life, and environmental issues. Environmental issues due to the lead. We know the lead is, I mean, it's quite toxic. So it has some environmental with respect to the discharge and all. And one more problem here is we have the self-discharge rate. It has a high self-discharge rate, and it has lower life, only 3 to 5 years. The lifespan of lead is around 3 to 5 years, and even the volume requirement is very high. What do you mean by self-discharge rate? It has, as I mentioned, lead acid has high self-discharge rate. So sometimes you may not use the battery, but it dies out. Even if you don't use a battery for a long time, it dies out, died off. So that is what we self-discharge rate. So the second variant is nickel metal hydride. It has high energy and high power density when you compare with the lead acid batteries, and relatively safe in terms of the because here we do not have the lead, so there is that advantage will be there and can be discharged completely. High charge and discharge rate, environmental friendly. Here also it is associated with some high self-discharge rate. This problem is again there here, and it cannot be operated over wide temperature range and suffers from memory effect and unsuitable for parallel connections. Memory effect means suppose if a battery is uh, charged to 100% and it has been utilized, next time it may not get charged to 100%. It may be some 98% or 95%. So there will be some degradation in the charging, maximum charging limit and all. So that we call it as memory effect. The third variant is lithium-ion batteries, which is a popular battery technology in utilization nowadays. So this is a popular battery technology. Is that it has high energy density, high power density, even longer life span when we compare with the previous two variants. Low self-discharge rate, no memory effects, high efficiency. But there are some constraints with the availability of Lithium is not, and one more issue is low recycling value. The lead acid and nickel metal hydrate, they are easily recycling is possible, but here it's not possible. And there are some safety and cost concerns. It's somewhat costly when we compare with the previous two. So yeah, again, in lithium ion, we have various types. So here we can see the battery technology used in various EVs from the year 1997. So it's mostly lithium ion. Beyond the 2008 and all, it's mostly the lithium ion. Previously, we used to use the lead acid based or nickel metal hydrate. But after 2007 or 8, it's completely dominance shown by the lithium ion batteries. Okay. Again, he can see the energy density and density. In terms of the energy density, also there is a significant increase over a period of time. Okay. And the battery rating also. So different battery ratings previously it's lower, and here almost around 85 or 60, even more is possible now. So these are the other battery technologies which are also available, such as sodium ion batteries and potassium ion batteries. But they are not that popular. These two technologies are not popular because of its poor energy and power density, because that is a major criteria. We want more energy density and power density. We want a lower compact size, and more energy density is required for EV applications, but these two technologies are not capable of. Lithium sulfone battery also, it has shown some potential with respect, as sulfur is cheap and it's non-toxic. This also being shown some potential, but again it's costly. So still research is being going on based on this particular technology. Solid state battery is based on the solid electrolytes, uh, and due to as they use solid electrolytes, they are more they have high energy density and relatively safe. I mean, they are more tolerant to high temperature. So like right now the more research is also focused on the solid state battery technology. Trends on EV batteries, battery swapping technique. This is one of the technique the researchers are thinking on to extend the range. See, one of the major limitation or one of the major drawback is with respect to the range, or many people are concerned about is, suppose if a battery with 100% charge, it can go up to some 200 kilometers. That is the range that is given by the company fetchers. So let us assume, okay, 200 means at least 170 or 180. So beyond that, suppose there is no charging station within your limits, so that will be a problem. So there is one battery swapping technique. So the battery can be removed and a new battery can be easily plugged in. So the old battery will be I mean, used by some other things. And so this battery swapping, simply just removal of battery and keeping a new battery, and it can be utilized for our EV applications. So this is one technique which is based on the solid state batteries, which is a promising technology, and it may replace the lithium ion batteries in future. So the researchers are working on this particular technique, and even they are utilized like by some companies like Ola and Uber for their basic customer transportation. Coming to the battery management system, we have some concerns. Battery management system, it's required. Why? Because we need to maintain, suppose if we consider the lithium ion batteries, we need to maintain the voltage and current. Even the temperature should be in safe limits or safe operating limits, we say. So violating these standards, it may degrade the battery performance or even result in some safety issues. And even though it's costly, so if it's performance degrade or it's damaged, again we need to replace the battery and it's cost. So we need to take care about that. So battery management system helps in maintaining the performance or improving the performance of your battery from damage, and it of course increases the lifespan to maximum extent possible. So these are the different types of battery we have. There is the from the construction point of view. So based on the application, they are being utilized. So these are the structure. So here you can see generally the battery pack. is generally kept at the bottom of the driver's seat. So whenever there is some a problem or any accident, such a type of thing, generally the rear end and the front end will get damaged. There is not much effort here, so that's one of the reason. Even there is a lot of involvement or research is going on with respect to the mechanical enclosure, mechanical development or thermal management. So thermal enclosure or mechanical enclosure is also equally important from the design point of view. Most of the mechanical engineers, they might have developed the CFD simulations with respect to the thermal management and all, so that the temperature does not go beyond a particular value. So battery packaging is also equally important. Okay, and batteries, as I mentioned, is generally placed here so that the center of gravity it's close to the earth. Okay, so even during crash and all, the impact will be slightly less. We are talking from the battery point of view. Okay? So that's the reason they are placed here. So this is what's shown here. Coming to the motor technology, the basic operational design requirements of the motor, the motor should have high torque by power density, high efficiency over a wide operating range, high maximum speed capability, capable to operate with wide constant power region around 3 to 4 times base speed, high torque for starting at low speeds and hill climbing. This is for a gradient application. Intermittent overload capability. At least for short duration, it should be able to support the overload, high reliability and robustness, and acceptable cost. So these are the basic requirements of the motor that you choose for your EV application. So these are the typical characteristics, motor characteristics we are talking here. So for some region, with respect to the speed, if we here it has a higher torque, and here for this particular region it has a higher efficiency. But in order to obtain higher efficiency is one of the major performance parameter which needs to be taken care. So if we operate your vehicle in this particular, if you try to operate the motor in this particular range, in this particular speed torque range, a high efficiency can be obtained. Okay. And these are the different regions, constant torque region. So initially for lower speeds, we may be getting constant torque region, and after particular speed we'll be getting constant power, and here the reduced power. So here, okay, this with respect to the motor characteristics. Coming to the load on EVs. So the basic load with respect to this, suppose if we consider a linear or a road load, here these are the various parameters like rolling resistance, climbing resistance, and aerodynamic drag. So all this needs to be considered while designing the motor. So first we'll be calculating the tractive force loads. So based on the load requirement only, we have to design the motor. Okay. So here we can see the climbing resistance and the rolling resistance are almost constant with respect to the speed. With respect to the speed, these are constant. They are not independent of speed, you can say. These two parameters. However, the aerodynamic drag is proportional to V square, velocity square. So that's why the profile is something like this. So the total resistance is profile is something like this. So whatever the motor you design, it should be rated. The rating of the motor should be designed in such a way that it should be able to meet or withstand the initial acceleration, cruising at rated vehicle velocity, cruising at maximum vehicle velocity. So here you can see, as I mentioned, for the lower vehicle speeds, generally you'll be having a constant torque, and here this is the region of constant power. So here we have the rated speed. This is the maximum speed that is possible. Okay, Vmax. So rated motor speed VRM. VRM is rated vehicle speed, and Vmax is maximum vehicle speed. So all these are different parameters. So what is the voltage that needs to be fed? What is the value of VRM? What is the rated voltage that is required? It's dependent on one person. So the ratio of constant torque to constant power plays a major role. So let us see in the next slide. In order to start the design criteria, we should design it such that it meets the initial acceleration. We know that alpha can be written as dv by dt, rate of change of the velocity we can write, which can be in turn written as f by m. So f minus fw divided by m, the mass. So if this particular term is taken on the other side, and if you differentiate on both the sides, sorry, integrate on both the sides, and if you do some mathematical analysis or calculation, this is a final expression. So this will be the final power requirement of the motor, PM, power required by the motor. It depends on the mass, TF, and other velocity values. That is the rated speed and maximum volts. So here we are interested in finding out the value of VRM. What is the value of VRM such that the power requirement is low? Obviously, we should design the motor in such a way that it requires a low power rating. See, higher the power rating, higher the cost, and higher the size. So the size and cost is directly dependent upon the rating of the motor. So this particular value we want minimum. I mean, we should select a suitable value of VRM such that the power requirement is low. So in order to do that, we have studied in mathematics. We can differentiate this in order to obtain the minimum value. So from this, if you differentiate the above equation with respect to VRM and equal to 0, then we'll be getting the corresponding value. So from this, what we understood is the constant torque, we get VRM equals to 0. So in this, if you see VRM is here, no? So if VRM is 0 means what? Constant torque region should be 0. Of course, practically it's not possible, but we should try to maintain in such a way that the ratio of constant torque with respect to the constant power should be as much low as possible or minimum as possible. Then the power rating of the motor will be minimum. So that is what we obtain from here. So this particular region should be minimized as much as possible in order to get a low power rating motor for the same specifications. So here you can see the ratios, 1:1 ratio. I mean, this ratio is constant torque by constant power ratio with increase in the value. So 1:1, the power rated power requirement is, I mean, the power rating is 110. So if you increase to 1/6, I mean, it's decreased. The value is almost 1/6 means it's low value, no? So here you can see the power rating requirement is significantly reduced when you compare with this particular rating when you adopt 1:1 ratio. Coming to the motor data, here we can use different types of motors like induction, PLDC, and SRM. We'll see in brief slightly afterwards. And here also you can see the power rating requirement, okay, with the power range 1:2.25 or 1:3. So 1:3, if you 1:5, if you take, the power rating requirements is very low, 65. So here 1:2.25, your requirement is 86. So this ratio plays a role in the selection of the motor power rating. Coming to the motor technology, so we use different types of motors can be employed. The first type is the brushed DC machines or the conventional DC machines. The conventional DC machines, the main advantage is control is very simple, easy to control basically, does not require any advanced electronics to control it, but it has some drawbacks in terms of the commutator and brushes. So it has some commutator and brushes which require some maintenance because they generally wear out and it requires some maintenance. So that is a major criteria. And one more thing, coming to the lifespan and the power density is relatively poor. So that's the reason generally the pressure DC machines are not employed for the vehicular applications for EVs. In EVs, mostly the induction machines or the permanent magnet based machines are utilized. So induction machines previously they are not that much popular for transportation purpose because they are difficult to control. But in later 1990s and all, they have been a separate algorithm was being developed. That is a vector control algorithm through which the induction motor can also be controlled, similarly like a DC motor. But the thing is, it's quite complex. The control is slightly complex. Anyhow, due to that particular algorithm, induction motor control is also become simple. Even though the control is complex, but it can be controlled in a simple way. So they have been used for even for the traction applications. Nowadays, we are utilizing induction motors. Previously, we used to have DC series motors, but nowadays they are mostly replaced by your induction motors. Coming to the efficiency of the induction motor is slightly poor when you compare with DC, and of course the control is a bit complex, so it requires some heavy technical skills to control the induction motor. Major attention is made the permanent magnet. These are getting popular nowadays for EV applications. In permanent magnet machines, we have the synchronous PMSM, permanent magnet synchronous machine, okay, and BLDC, brushless DC motor. So brushless DC motor is basically for two-wheeler and three-wheeler segments. Mostly they are getting popular for two-wheelers, whatever the scooters and all, even the rickshaws or autos. They're mostly based on BLDC machine. And synchronous PMSM, I mean PMSM is basically for the four-wheeler segment like cars and okay. And switch reluctance machines are also getting popular, which is based on the reluctance principle. But the problem with the permanent magnet is it uses a permanent magnet which is made up of the rare earth materials. The rare earth materials they are somewhat costly, and one more problem is they are temperature dependent. So beyond a certain temperature, the performance may not be good. And one more problem is they are not available in our country in a major scale, and they need to be procured. They needs to be procured from other countries like China and all. That is one more problem with the permanent magnet based machine. So we need to rely on them. But from the efficiency perspective, they are very good. PLDC, the control is very, very simple. That's the reason they are getting popular for two-wheeler and three-wheeler applications. And these SRM missions, these SRM based can be used in off-highway vehicles where noise and vibration is not a constraint. So here we can see the comparison of different motors on a scale of 1 to 5 with respect to different performance parameters. Coming to the efficiency, here you can see DC motor it has low efficiency, but all other motors like induction motor, PM motors, and SRM, they have better efficiency. So maximum rating is 5 actually. DC motors, the major advantage we get in terms of control. Control is very simple. This is the major thing it takes advantage, but all other performance parameters, if you see, weight by power density, cost, torque by ripple, and one of the problem with the SRM motors, if you observe, it has high torque ripple by noise. That means there will be some vibrations during its operation. So that is the major limitation in SRM. Other than that, if you see, it is also mostly suitable for EV applications. Keeping that particular criteria, if that is the only major limitation. So majorly, if you see induction motor everywhere, it has in terms of all the performance matters, it has better characteristics. Similarly, PM motors also. So that's the reason these two, that is induction motors and permanent magnet motors. In permanent magnet motors, again we have BLDC and all these things. They are mostly getting popular for EV applications. Coming to the sizing of EV powertrain components. So here a prototype, typical cart type vehicle is being replaced, in which these are the components in which we use a FPGA, a battery pack. It's basically a battery-based electric vehicle. Previously, it's a normal vehicle planned to convert to a battery type electric vehicle. So these are the various components. As it's a low power based vehicle, so BLDC is more than sufficient, which are around 20 kilowatt. And the power converter, it's basically depend on IGBT based inverter, and these are the various components. So coming to the vehicle specification, first of all, in order to design the motor and other components like power converter and all, we need to know the vehicle specifications such as mass, max velocity, acceleration, and other these coefficients like rolling resistance, drag coefficient. All these things need to be known. So these are the various parameters that is specified for the vehicle. So from this, we can start designing the motor. Step one is compute the track to effect, overall track to effect or force, net force that is acting on the vehicle. So from the load point of view, we can calculate these things. Compute the torque on the wheel and the motor. Compute the RPM of the wheel and the motor. And from that, we can calculate the overall shaft power of the the motor and scale it up by a safety factor. So let us start from step one. So in order to calculate the overall tractive effect, we need to consider all these parameters like rolling resistance, timing, and aerodynamic drag. So at a particular point, we have taken at this particular point the different parameters we have considered, and all these values are already given from the table. Simply substitute, and if we add all these things, we'll be getting the overall net tractive force that is required. That is 3380, and for this particular case, this is a basic procedure for designing, but from the industry point of view, it may be slightly differs, because here we have considered for a particular condition we are calculating here, but this is the basic procedure. Wheel angular velocity by RPM can be calculated here, and from this it can be converted to the radians. Similarly, wheel torque. So here R means the radius of the wheel. Similarly here, here R means RPM. Torque on the wheel can be calculated F net into R. So 3380 into 0.36. So we'll be getting the wheel torque, and from the wheel torque, considering some gear ratio. If you consider some gear ratio and all, where the motor angular velocity can also be calculated by considering some gear ratio. So from this, the overall motor torque can be calculated. Once this is calculated, the torque, wheel torque from the wheel torque, considering the efficiency and the gear ratio, the motor torque can be calculated or computed. So motor power rating, here it's we know the motor torque. So motor torque into omega of motor, if you multiply this, we'll be getting around 17 kilowatts. So considering some safety factor, generally 17 means we generally consider higher rating as a part of safety. So 20 kilowatts can be considered. So the similar value can also be obtained. This particular expression we have seen for design the motor previously. So this expression can also be utilized to calculate the same thing. So even if you do that, we will be getting around the same value. Motor sizing, motor power rating for accelerating the vehicle to rated speed is given. We have seen this particular expression. This is a motor power rating. Suppose if we consider VRV as 40 kilometer per hour, if we convert it to meters per second, and if we substitute, so K value and this M and TF value, if we consider, and if you substitute, we'll be getting around the same value. Okay. So finally, we have considered a 20 kilowatt PLDC motor, and these are the motor parameters. Power is 20 kilowatt, voltage is 96 volts, current is 208 amperes, and maximum utilization is point. Similarly, battery pack sizing. So based on the requirements, we can also calculate this lithium-ion batteries. So as a part of thumb rule, 250 can be considered for a particular per kilometer. For 1 kilometer, 250 watt hour is required. This is a general rule. So based on this, for 80 kilometers driving range, we can calculate the overall requirement. And minimum battery pack voltage is 96. We have considered for the battery 96 volts. So 96 divided by 0.8 is 120 volt. So based on this, suitable series and parallel combination can be calculated, and the DC link voltage requirement can be easily calculated. Coming to the inverter rating, the power rating of the inverter is generally selected as 5 times the motor rating. So it should be around 100 kilowatt, so that it can be able to withstand for different conditions, overloading on whatever may be the transient conditions and all. In inverter, generally we'll be having the IGBTs. IGBTs or MOSFETs, but inverter mostly will prefer IGBT. So the voltage rating of the IGBT should be 5 times the maximum DC link voltage, so around 875 volts. Current rating can be calculated accordingly based on the power level. So power level is 20 kilowatt. 20 kilowatt divided by 120 based on the battery pack. So this can be calculated. So again, here also we need to consider some safety factor. Even though these are the ratings, voltage and current rating, we will be selecting generally higher value, so that it will be able to support even during the transient conditions. Transient conditions means whenever we start or stop, there will be sudden increase in current that flows through the various components. So that parameters also will be taken care here. So that's why we select a higher rate of voltage as well as. So these are some of the available EVs in our market. So all these models are available even in India. So Tata Nexon EV is getting popular. I mean, many customers have been buying this, and there are some other models also. If you see, most of the models they're using induction motor type. So induction motor type or PMS in this case. And you can also see observe the motor rating. Motor rating, even Tesla nowadays it's very popular company in US and all. Even they have the here you can see the power rating. They use two motors. The power rating is very high. So due to this high power rating, the acceleration is also high. Acceleration is also one of the major component parameter. Suppose it's this particular model may be able to reach 100 kilometers per hour maybe within some seconds. So that coming to the battery type, you can observe mostly they're using lithium ion battery or lithium polymer. These are some of the battery specifications. So their motor rating. So here there's a higher power rating, and here also Mercedes Benz also 300 kilowatt, which uses two motors. Maybe some sharing 150, 150. Even the battery specifications also you can see here they're using 100 kilowatt hour. So more the power rating, more the battery specification, battery rating should also be there. So coming to the challenges in here as a part of this particular discussion. So here you can see the gasoline biodiesel have higher energy density when you compare with other sources of energy. Similarly, the lithium ion is completely very low when you compare with the energy density point of view. It's very low. So for this particular reason, this is a major drawback in the lithium ion battery when you compare with other sources of energy with reference to the energy density. The same thing can also be repeated from this figure. So one gallon of gas is equivalent to 135 megajoules of energy. So the same thing if you want to obtain, same energy if you want to obtain from the equivalent lithium ion battery, this much size is required. So obviously, this is a very huge size. This much amount of size or weight cannot be kept in your EVs because more the weight, it impacts the performance of the vehicle. It's not feasible. So here you can see from the here 2.75 kg equivalent, but here from the battery, if you calculate the overall weight, it maybe corresponds to around 340 kg. So this is one of the major drawback in lithium and battery technology when you compare with the. So research is going on to improve the energy density such that this weight is should be drastically reduced. So these are some of the challenges still we are facing. Slow charging time. So we have seen the onboard charger and offboard charger. See, onboard charger, it takes some 7 to 8 hours maybe for charging, depending upon the battery rating. Okay. Battery life. Battery life is also one of the constraint. Previously, we used to have only 3 to 5 years battery life, but now it's slightly extended to up to around 10 years. So in future, still research is going on such that the battery life may be extended up to maybe 15 years or so. High initial cost. The cost of the EVs are even in the market, if you compare, it's more than 10 lakhs. Most of the vehicles, it's more than 10 lakhs. I mean, low-end vehicle itself is more than 10, 12 lakhs, 30 lakhs. Limited range. Range is, of course, now there is an improvement in range. Slowly, the range is getting increased, but still, maybe some 300 kilometers range or maximum 500 kilometers is possible. Not so maximum range it should increase. Grid integration. Maybe in some areas, suppose the utility or grid is not available, again it will be an issue. And in some of the vehicles, as we mentioned, we are using the permanent magnet motors, no? Where we use rare earth materials. So that is also costly, and we need to depend on some other countries for its procurement. Reliability in power electronics. Mostly the safety concerns and all things will be taken care. However, if due to some issue there is a failure or damage to some component, power electronic component, again it will be an issue. Consumer acceptance. So still people are worried about the operation and its usage. So still the automobile companies should ensure and try to get the acceptance from the consumers. Anyhow, due to the increasing petrol and diesel price, we are slightly focused or paying some interest towards it. So let us discuss some other aspects related to this. Again, you already seen the system architecture of EV in previous slides, but this is a brief version where this is a grid. And here in this model, the major component is battery, which needs to get charged. So that's the basic thing. So here we are using some lithium-ion battery, which is obviously of some high voltage, some 230 volts or 320 volts, whatever. It needs to get charged. So here, in order to get charged, here AC is basically grid is basically AC. So we need some conversion, power electronic conversion. So we are converting AC to DC here, and this DC is converted to this DC can be directly fed, or sometimes again here we have some conversion, some DC to DC conversion, basically high frequency conversion, and finally this battery is being connected to this. And here you can see some other auxiliary components like headlamp, dashboard, music system, airbag, all these things. These things also require some low voltage like 12 volts. So again, this is the main battery system. Here we have some another converter which we call it as push-pull converter, which reduces or step down the voltage to 12 volts, and it's given to this voltage is utilized for this particular auxiliary components. And here, as we mentioned, suppose let us assume we are using induction motor, which is basically AC motor. It requires some AC supply, but your battery is DC in nature. So again, here we need to convert from DC to AC. So how to convert? One such possibility is we can convert DC to DC. I mean, we can boost the voltage, and this voltage can DC voltage can be converted to AC by using a inverter. It may be a three-phase or single-phase inverter. So here you can see this is nothing but communication lines. So whenever you connect the your vehicle to the grid, there is some communication port which estimates the state of the battery, state of charge of the battery, and based on that, it communicates with that, and accordingly it gets charged. So from this slide, it's very clear that there is a definite requirement of power electronics here. From the battery to the motor, in between, we require some power electronic conversion. And one more thing is, it should be bidirectional nature. We have discussed different modes of operation of OBC, or onboard charger. So there we have discussed grid to vehicle, vehicle to vehicle, different modes. So sometimes a part of the energy from maybe fed in this direction during regenerative braking and all. That's why this particular converter should be bidirectional in nature. That also needs to be taken. 1 second. So this is the basic difference between the onboard charger and offboard charger. One basic difference is here you can consider some 5 to 6 kilowatt, the value. Here it will be somewhat more, maybe some 12 kilowatt or even more. I mean, sorry, 50 kilowatt. So that we can consider. So based on the power rating only, the charging will be dependent.
Excuse me, sir, you have muted yourself.
Mistake, I think. Yeah, sorry. Yeah. So the only difference between the offboard charger and the onboard charger is the power level. So onboard charger, the maximum how much we can get utilizes 3.3 kilowatt to maximum range of 12 kilowatt. So onboard charger is present in the vehicle itself. So we cannot go beyond a point. If we go increase the capacity or rating beyond a point, It increases the size of the vehicle, and of course, there will be some safety concerns also. Basically, it adds weight to the vehicle, which may degrade the performance. But here, off-board charger means we might be having some charging stations, and there your vehicle can be connected, and so that it can be charged in a less amount of time. So suppose here it's taking some 7 to 8 hours, but this you can charge in your home itself. So 7 to 8 hours. Here the time requirement may be some 15 to 30 minutes. So that's the advantage you get here. So in future, you might see some charging stations instead of petrol pumps. You might see some charging stations everywhere where your vehicle can get charged within some 10 minutes or 15 minutes, and it can be simple. Okay. So charging time is one of the constant here. Okay. So just now we have discussed the necessity of power electronics, to feed the motor or any other application. So basically, it requires some battery management system, some DC to DC bidirectional converter, VFD, variable frequency drive for electric machines, and DC to DC converter for auxiliaries. Here also we require some conversion by using some push-pull converter. So let us see the different power electronic things. Before going to that, these are the typical types of charging power levels. We can use AC charging or DC charging, depends. So here you can see the DC charging where 200 to 450 volts, and this is the power level and voltage levels which can be utilized, and DC rapid charging. These are the different power. So we have some standards, internal standards that needs to be followed with respect to the EV applications. These are the different things. So coming to this particular thing, the main objective here is to charge the battery. So this is your utility or grid where we have the AC. So here we require DC. So we are converting first AC to DC. Again, see this DC, you may think that this DC can be directly given. Already we are converting AC to DC. Directly this can be given. But the thing is, this battery pack, suppose it requires some 300 volts, let us assume. Here, suppose it's some 11 kV, for example. Okay. So whatever the value here, whatever we get here, this we call it as a rectifier basically. So whatever the voltage we obtain here, it may not be purely constant. That is one thing. So the required value will be obtained through another conversion, DC to DC conversion. If you use one more conversion here, you will be able to control it more properly. There's one more thing. Okay. So that's why here we are using two conversion, two power stages, AC to DC and again DC to DC. So whatever the value here, suppose let us assume here we are getting some 1000 volts, for example. Whatever the DC we get here, 1000 volts, but here we require only 300 volts. So again, we need to step down now. Step down the voltage. That's also possible. We can step up the voltage, step down the voltage. Here we have some different converters where we can regulate, increase or decrease the voltage accordingly or suitable. Okay. So based on the requirements. So let us see the different power converters. Suppose here we have some AC grid. Finally, we want DC voltage. As our battery requires DC, we want DC voltage. So how we can obtain, these are the different methods. So this is a typical charging station in which you can consider this a three-phase AC. Okay. You have a transformer, power frequency transformer. Power frequency transformer is 50 Hz transformer. Okay. So basically, we use a transformer to step down the voltage here. In this application, we are using it to step down the voltage. This AC is again AC to DC conversion happens here, and finally here the DC voltage is used by diff. So here, if you observe, we have different charging plugs. Here you have one plug. So this can be used for one vehicle. This can be used for another vehicle. Okay. So two vehicles can be simultaneously charged using this particular setup. Okay. This is one such configuration. Another possibility is, again, here you have a three-phase grid or AC. Okay. Here you can see individual setups. Here you have a Wiener rectifier. We will see afterwards. Basically, it's a AC to DC conversion. It's a rectifier. Again, DC to AC here. Here you are employing some high frequency transformer for the isolation. Okay. So the major advantage you get here is you have isolated. You have different charging pins which are completely independent. This complete thing can be considered as one particular unit. Okay. So simultaneously, you can charge n number of vehicles using this particular charging station. So all are isolated. It's not dependent on any other thing. Okay. So why we are using this high frequency transformer is for isolation. Isolation is sometimes very important uh, whenever we are dealing with some high voltages and all. So that there will be no leakage issues and all. Anyhow, that's somewhat related to the PV panels and other things. So coming to this, the first thing what we require is AC to DC conversion, which is possible by this particular configuration we want. This is a typical three-level three-phase NPC converter. Okay, and this is generally used for high power ratings. Okay, we have some advantages. Basically, this particular concept we call it as the multi-level inverters. It has some advantages compared with the normal inverters. So basically, from the basic point of view, we can say the multi-level inverters are suitable for high power applications and high voltage applications. And we have some advantages in terms of lower dV by dt rating, stress. The stress across the switch is reduced, and we will be having a better performance. Even the filter requirements are reduced. Suppose if you compare a simple inverter, conventional inverter, the filter requirement is more. But here, with the multi-level inverter, the filter requirement is considerably reduced. Okay. Even the waveform quality is also improved. But the thing is, here the drawback is you need to take care about the balancing, the capacity balancing you need to take care. I mean, they should be equal. It should be equal. So neutral point balancing, it should be taken care by suitable control strategies. This is another such configuration where you can convert from AC to DC again, the same thing. The advantage we get here is due to these inductors here, we can able to boost. So whatever the voltage here in previous configurations, it simply converts to DC. But here, due to the inductors, it's able to boost the voltage also. So there's one more advantage you get. This is another Veena rectifier, which also converts AC to DC. But the advantage we get here is it has the bidirectional feature. Here you can observe the bidirectional switches. Basically, this is a bidirectional switch uh, where the current can flow in both sides. If there is a requirement here, the current can flow in this direction. Suppose there is excess energy here. As we discussed, we have the regenerative braking. No? In regenerative braking, part of the energy is fed back to the source. So this is your source. In regenerative braking, part of the energy is fed back to the source. So in that case, what happens? Suppose let us consider this is the source, and here you have some excess energy. So the current will flow in opposite direction. The power flow, generally the power flow direction is from the source to the load. But during some braking, regenerative braking, the power flow may be in opposite direction. So part of the energy is saved. So in such conditions, you require this type of rectifier where it has the bidirectional capability, bidirectional power flow. So this is one such configuration. So till now we have seen AC to DC. So in between, if you have observed, DC to DC is also there. No? So here you can see from the grid. Initially, we want AC to DC. Again, DC to DC converts on. So let us see some DC to DC configurations which are generally utilized. So this is your DC voltage, whatever. So here we are using some high frequency transformer. High frequency transformer. Why we are using high frequency transformer? Why? Because generally the size of the magnetic components or the size of the transformer, if you want to consider, is inversely proportional to frequency. So higher the frequency, lower will be the size of the transformer. So that's the reason, as we discussed in electric vehicles, size and weight are one of the main component. I mean criteria. Obviously, we require lower size and lower weight. So that's the reason generally we use high frequency transformer. Sir, is it audible, sir?
Yes, sir, it is audible.
Actually, here there is huge heavy rain, sir. Due to that, some power cut is there. Okay.
Yes,
Anyhow, now I'm trying through mobile net, sir. Okay, sir. That's why. Okay. So the size of the transformer is inversely proportional to frequency. That's the reason here we use a high frequency transformer. Okay. And this is a dual active bidirectional DC to DC converter. Similarly, we have some other configurations similar to the previous thing, but here we have some resonant DC to DC converter in which we have some advantages in terms of the soft switching. So here we use a soft switching technique such that the overall switching losses will be reduced. That is the advantage we get through the soft switching. And here also we generally use very high frequency. And one more advantage is here the electromagnetic interference will be low EMA and high efficiency. So push-pull converter, you might have observed this particular configuration we are using for the charging of the auxiliary components like headlamp, airbags, and all these things, where the output voltage, you can say it's only 12 volts. 12 volts is required. But here, you might have seen this is your battery voltage. Battery voltage is relatively high now. So it may be some greater than 200 volts or so, depending upon the type of vehicle. So 200 volts, it needs to be stepped down. We need to reduce to 12 volts. So this is one such configuration where it's possible. As here we have a transformer. So transformer generally based on the turns ratio. By decreasing the turns ratio, we can reduce the voltage accordingly. Okay. So at this end, we are getting AC. Again, by using some diodes, finally we are getting the DC voltage. So this is the push-pull converter, which is isolated basically. Isolated means as we are using a transformer, we call this as isolated DC to DC converters. So till now, in our discussion, wherever we have seen the multi-stage conversion or two-stage conversion. Okay. So sometimes due to this two-stage conversion, there will be a reduction in efficiency due to the more number of components. So we can also go with the impedance source inverter, where we have a single-stage conversion. Okay. So that's the advantage we get here. So even the impedance source inverters can be utilized for your EV applications. So this is a jet source inverter in which, as I mentioned, so this particular voltage you can consider it as battery voltage. Okay. So finally, ultimately, we want to convert DC to AC. That is our major requirement. As mostly the motors are based on the AC supply and your battery is based on DC. So how to convert DC to AC by using jet source inverter? We'll see briefly. So it has some features in terms of the buck boost capability. Buck boost capability means whatever the voltage you give here, the DC voltage, it can be boosted, it can be increased, and it can be converted to AC. And we have some other advantages in terms of the reliability. That means generally in any voltage source inverter, no two switches of the same length will be gated on simultaneously. But here, that particular feature is utilized in order to get a better boost gain. So this is the control technique we adopt for controlling of that impedance source inverter. So there is a slight variation or modification that needs to be done in the conventional carrier-based PWM such that the shoot-through is inserted in the zero state. Okay, so that we'll be getting the. So these are the equivalent circuits during the active one shoot-through state. Here the main concept lies in the volt-second balance. So from this we can calculate the DC link voltage. But here the major limitation is with respect to the discontinuous input current. So that's the reason we generally go for the quasi-jet source inverter, where it has continuous input current profile. So in case of EV applications, generally we require continuous input current. There should be no discontinuity. Okay. Suppose if we even if you use fuel cell or battery, whatever, there should be continuous flow of current to the motor. Otherwise, the performance will be degraded. So multi-level features in terms of the better quality of output voltage and output current, reduction in filter size due to the more number of levels, Because multi-level inverter waveform, it's the waveform output waveform if you observe, it's almost close to sinusoidal waveform. That's the reason the filter requirement is slightly reduced. Even better electromagnetic compatibility will be there. So this is the classification. However, we have some limitation multi-level due to the buck nature of the output voltage. So due to this, we have worked on the combination or integration of impedance source network with multi-level inverter. So this particular combination or integration can also be utilized for EV applications. However, I have done for the grid-connected applications. But now I'm investigating or doing research for the EV applications also. So anyhow, this is a part of my research work. Due to the time constraint, we are skipping here. This is one such configuration in which we have developed based on the PUC inverter. This is a packed usual 7-level inverter. And again, here also we have used a high frequency transformer with multiple secondary windings. So here, instead of grid, we can also utilize it for the EV applications. So we have developed a new control technique, and this is the overall prototype. As this for grid connected applications, we have connected with the respect to the load and all. Okay, and I have utilized FPGA processor for its control operation to control the various switches and all. We have used FPGA, and these are the final results of your 7-level waveform. So let us actually during my PhD research, one of my mechanical colleague, he has worked on the I mean, he is also from mechanical background, and he worked on the fuel cell hybrid vehicles basically. Uh, then I used to assist him in some aspects of the electrical technology. So basically, electric vehicles nowadays, all branches are working. It's an interdisciplinary topic, both electrical and mechanical also, all are working. So basically, I will try to share some of the things what he has worked actually. It's not my work, but I will try to. So it's a fuel cell based hybrid vehicle in which here hybrid means it's a combination of fuel cell with some battery and ultra capacitor combination. Okay, not we as we discussed in the starting, it's a different thing. Here it's a combination of fuel cell, so it's a pure electric vehicle. Okay. So here the major work was based on these are the various things. I mean, majorly the fuel cell stack, battery, and ultra capacitor. So it's a combination of both these things have been utilized. So one of the work is majorly focused on by using the advisor software. I think you might be you mechanical engineers might be knowing well than me. He has worked on an advisor software, uh, which is directly it's nothing but the MATLAB simulating software. If we install this advisor software, it's directly we have a separate toolbox through which we can connect the different things. And the major thing is the major advantage here is uh, we get a customized model. We get a direct model. So this is the advisor's block diagram. This is a complete block diagram using Simulink, and we can customize based on a requirement. Generally, electric vehicle means it needs to be tested under different operating conditions or different drive cycles. You can say we will be having different drive cycles. No? It needs to be tested. So this is the overall model, and here we have some different options where we can select our required things, fuel cell combination with battery or whatever. You can select accordingly, and you can test for different drive cycles. That option is there. So those who are not aware, you can try it out. So this is one such area or where you can explore. As this is purely related to mechanical engineering, I thought of slightly discussing this, which might be useful for some of the researchers. So I will try to share part of it. This is the specifications of the vehicle, and we have a hybridization ratio, where it's a ratio between the energy storage, the power to the energy storage divided by the overall power. Overall means energy storage plus the fuel cell power. So for different hybridization ratios, the fuel cell requirement changes. This is a change in the. So suppose if you consider 0, so it's completely fed by the fuel cell. As you keep on decreasing the fuel cell power rating and increase the ultra capacitor rating here, this is a variation of the hybridization ratio. So we have different cycles, drive cycles like urban drive cycle, highway cycle, and all these things. Uh, You need to test different performance parameters under with respect to this. So one such work I thought of sharing here. So which is a part of the downsized vehicle. So here, what he has exactly done is try to reduce the power rating of the fuel cell stack and increase the batteries correspondingly. So here you can select your different things, energy storage 1, 2 you have, and you can select here accordingly. So downsizing criteria. So here the fuel cell power has been decreased significantly, and accordingly here it's reduced from 114 kilowatts to 57 kilowatts. Okay, and the correspondingly battery capacity is doubled for the same motor power demand. Okay, so it's compensated with the battery. So this we call it as downsizing criteria. And through this technique, he has compared with the commercially available Toyota Mirai fuel cell based hybrid, which is commercially available in the market. So he has compared the performance of this downsized vehicle with this with respect to different parameters, and is able to achieve a better performance. For different cycles, he has compared the speed, battery SOC, power output, and different all other parameters also, like energy consumption. These are the different performance, like energy consumption for different parameters. For both the things, for Toyota Mira vehicle and downsized vehicle, they have compared. And finally, fuel economy, driving range. So finally, here you can see the comparison, performance comparison with respect to the downsized vehicle, which he has designed, and this is the commercially available vehicle. And almost there is a almost close performance has been achieved. In some cases, a better performance is also achieved. So almost close in terms of fuel economy, acceleration performance also it's slightly less here. Less time is required, to get the required acceleration. Driving range is almost same. So this is the advantage. And compared to the cost also, it's significantly decreased. So this is one such work actually. So he has extended the same work for other combinations. This work is basically for the ultra capacitor and fuel cell combination. The same thing can be extended for the other things also he has done. So those who are not aware or looking, they can look into this particular area, which is nothing but the energy management of the hybrid fuel cell based electric vehicles. They can utilize this advisor software and develop things. So this might be useful for some of them. That's the reason I have discussed this. So thank you very much. This is my presentation.
Thanks, Jammy.
Yes, sir.
So we have few questions from the participants.
Yes.
So I would like to begin with few of them.
Yes, sir.
Yeah. So the first one is, what do you mean by AC chargers? Is it taking the help of inverters for battery charging?
1 second, sir. I'm unable to.
Yeah. Shall I repeat it?
No, sir. I'm unable to see. Actually, coming to the actual thing, I want to stop sharing, but okay, stop sharing. Yes, sir. It's fine. Okay, sir. Yes, sir. What is the AC charger?
Yes.
AC charger. I mean DC onboard charger. I've discussed there. AC charger means which uses the AC supply. We have two types of basically DC supply, AC supply. AC charger means which utilizes AC supply. That's all. Basically, two types we have: onboard charger and offboard charger. The onboard charger basically the charging station which has some higher power rating. Offboard charger means nowadays we are using some scooters and all which they are using, getting charged in the town. Even in our apartment, some might have purchased that e-scooters EV. They are charging through that offboard charger. We have some power cable and it's similar like mobile, nothing else.
Okay.
Same like mobile, but it's taking time. See, our mobile will take some 1 hour to get charged to 100%. But EV, as it's a more battery capacity, it requires some 7 to 8 hours maybe. So, okay, in home it's okay, but if you go some outside and if you are getting stuck in the traffic or somewhere in different location, and you don't have any access to the power, then that will be a problem. So in such cases, we can go with off-board chargers, where you have some charging station. Nowadays, Ola is developing such charging stations.
Okay.
where you can charge your vehicle. Yeah.
Yes. The second question is, can you please elaborate on torque power ratio? How to minimize?
Torque power ratio we have discussed with reference to the motor selection, motor
Yes.
power rating selection. So we there the main thing is that particular ratio, if it is decreased, the main advantage we get is the power rating is also decreased. I mean, if the ratio is decreased, low power rating motor can be employed. So that's an advantage in terms of cost, obviously. So in order to that is a design criteria. Why we have done that is we have calculated. If you have seen the derivation, we have calculated the minimum value, minimum voltage for that particular voltage. Minimum power rating motor is designed. So based on that ratio, it's dependent actually.
Okay. I hope you answered the question. Third question is, can you please explain VRM and VRV?
Okay. VRM is basically the rated voltage. Here you can see the, one second, I'll try to share the screen if possible. One is rated voltage and another one is the maximum value. In the graph you can see, I think, yeah, here maybe. Yeah. See, VR is with respect to the motor rated. See, motor will have some rated speed. This is with respect to the motor's rated speed. VRV is with respect to the complete vehicle.
Okay.
So vehicle is different, motor is different. Of course, this should be almost close. Vehicle speed, it may be slightly higher. This is the rated vehicle speed. And this is a maximum vehicle speed which can be obtained. So this is with respect to the motor and this with respect to the overall vehicle. See, we are discussing with respect to hybrid model. No? Hybrid model means what? It may be you might have some additional IC engine also. So by motor, this is the maximum velocity that can be vehicle speed that can be obtained. That's fine. But if you are using IC engine also, due to that also there will be some additional. So both are different. Let us consider this a hybrid vehicle. So through that IC, you are getting some additional speed of some 60 maybe. So additional, this is vehicle speed, is motor speed. So both are different.
Okay. So the next question is, why the power rating of inverter is 5 times motor rating?
See, just for the design criteria, see, whenever you might be knowing that during the starting and stopping of the motor or during any transient conditions, the high current is being drawn. Suppose if you consider induction motor, during the starting of the induction motor, a high current is being
High
drawn.
current. Yes.
So that high current obviously will flow through the inverter switches. So just for a safety constraint, so whatever the switches you select, it should be able to withstand such high current. So that's the reason we consider almost 5 times more, such that even the switch selection also will be such that it will be able to withstand during all conditions, transient conditions, steady conditions. It should be some higher value. Even if you consider 10 times, it's not a problem. But the thing is, higher the rating, the cost will increase. So that is also there. So basic design criteria that's adopted in most of the journals and all, it's 5 times. Okay.
So I think he wants to know about any standard that we are using. I think so.
Specific, no standard, no specific standard, sir. But as of now, what I know, but
Standard practice, we can say.
yeah, standard practice, sir. General convention or standard practice.
Standard.
Yes, sir. General, yeah, thumb rule type, sir.
Yeah. Thanks. That's it. Next question: which is the best motor to be considered for EV application?
Sir, that's what, sir. Here we have discussed this different possibilities we have seen. Suppose if you consider for two-wheeler segment, two-wheeler or three-wheeler segment, BLDC is most generally used. And for four-wheeler, we are going with induction motor or PMS. So here we have seen the different possibilities. So BLDC is for two-wheeler and three-wheeler, and induction machines and permanent magnet is for So based on the application, sir, based on the application, and SRE is for half EV vehicles. So based on the application, we should choose a certain type of motor.
Yeah, related to same, sir. So, can you please explain SRM?
SRM is switched reluctance motor, sir, which the principle is based on the reluctance, actually, the minimum and maximum reluctance. It's a type of motor. It's come under special missions, sir. We have a subject in electrical by the name special missions, uh, where we have different types, like the SRM, BLDC, stepper motor. Stepper motor is used for some robotic control applications, no, sir. These are the things. Yeah. But this is not popular, sir. Popular is induction and BLDC. These three are popular. SRM is not that popular. Still, so that's why I have highlighted these two things. SRM, there is a constraint in terms of the torque ripple by noise. The vibrations will be there. More noise and vibrations will be there. That's the reason it's not preferred for normal applications.
Okay, so the last question is advisor software is only for hybrid system, that is fuel cell and supercapacitor?
I didn't get you, sir.
Is advisor software
Yes,
is
sir.
only for hybrid systems?
Yes, sir. Of course, it can be customized to pure EV fuel cell, but basically it's for fuel cell, sir. Fuel cell based hybrid electric vehicles.
Fuel cell based.
Fuel cell based, sir, basically.
Okay. Okay, Dr. Jammy, thank you so much. You have answered most of the questions. And thank you for this informative session. I just like to call upon Professor Nikam to just to propose the vote of thanks.
Thank you, Dr. Jammy Rahul, for the detailed illustration of electrical vehicles, as well as the illustration of batteries and inverters and its application in electric vehicles. I'm sure that the deliberation which you have done today on electric vehicles and batteries will help the participants in their future studies on electric vehicles. On behalf of Shah Institute of Technology, I'm so much thankful to you for your today's session. And at the same time, I'm thankful to all the participants for their involvement in today's session. Before I declare that the session is over, I would like to request all the participants to keep your cameras on for photo session. Please.
Sir, I also don't know. But there is, as I mentioned, there is some problem with my, I think it's dark now, sir.
No, sir, it's okay, sir.
Okay, no problem.
Yeah, yes.
Nikam sir, done.
Thank you, sir. The link for feedback is there in the chat box. So we announce here that the session is officially over.
Sir, thank you very much, sir. Thank you for giving me the opportunity, sir. And I tried my level best to convey my things to the participants. As initially I was worried, as it's for a mechanical department and I'm from electrical, I was slight worried, but I don't know. I have tried my level best, sir, to convey my things. And thank you very much, participants, for your patience and everything. Thank you.
Yes. Thank you, sir. Thank you once again.
Thank you. Thanks.
Sir, can you have their email IDs for any correspondence, please?
Yes, I will share.
Sir, thank you. If email ID can be shared, thank you.
Hello.